In this class, we'll be using truth tables quite a bit. Therefore, it's important to properly construct a truth table to get valid results as we apply techniques that involve truth tables later on in the processes that we use to design circuits in digital logic. So here's how a truth table should work. First of all, what you're going to do is you're going to put Boolean variables across the top of columns, okay, so A, B, and C. And these should be put in binary order. So in this particular case, I have three variables, A, B, and C. The number of combinations that you can have for these variables will be 2 to the n. In this case, n is equal to 3, so I have 8 rows inside the truth table. These should be constructed in binary counting order. We haven't formally discussed binary, but it's not too hard. What we're going to have is a binary assignment to each column. This is the least significant bit place, so we have 2 to the 0 as the place value, 2 to the 0 as the value of 1. And then I have 2 to the 1 on the B variable, so 2 to the 1 is 2. And then I have 2 to the 2 on the A, that's the most significant bit. And so when we walk through all these binary assignments, you get these values showing up for the various rows. So all zeros is 0, 0, 0, 0, 1, that's binary 1, binary 2, binary 3, and so forth. All right, so we're going to be using binary a lot. You'll get to where this becomes really automatic. So you put all the variables across the top, you assign a most significant bit, a least significant bit. Normally that's in alphabetical order if we're using alphanumeric variable names. Okay. Next, what I want to do is show you some special case truth tables and walk you through how to interpret sum of products and products of sums. Okay, so this first one is a sum of products representation. I think you can see why it's called this. Product is not really the right word, and sum is not the right word because these are really ands and ors. So when we do a product of things in digital logic, we really mean anding of things. But the algebra connotation and the Boolean algebra, they're very similar. And so we think of and as a product and sum is the or. All right, so let's take a look now at A, B bar. All right, so notice the first thing here is I'm going to be in this course using a mix of using a prime for a complement, and sometimes I'll use overbar for a complement. I just want you to see it both ways, so I'm going to flip back and forth between how I use that. Okay, so in this case I have A, B bar, and if you look at where that is true when A is a 1 and B is equal to 0. When A is 1, B is 0, A is 1, B is 0, that's when that term turns on. Okay, everywhere else, that would be a 0. All right, so we build this out. In the next step, we would look at this product term, A bar, B, C bar. The only way you can get this to be turned on as a 1 is on a 0, 1, 0, and that then turns that on as a 1. From there, we're ORing these two columns together. And so our next step is to go ahead and every time we see a 1, we put that on out through the output and we get the truth table for this sum of product expression. Okay, so there's a similar thing that happens with product of sums, but it's slightly different thinking. Humans don't naturally think as well in product of sums as we do in sum of products. So we'll tend to emphasize sum of products more often, but product of sums is a valid form that's used quite a bit in digital logic. Okay, so let's think about A or B, all right? This is an ORing function, and so the only way you would get a 0 for this first term is if both A and B are zeros, all right? So I like to think of product of sums as identifying the places where zeros occur in the Boolean function, okay? So A or B, we would build that out. It would have that first row populated with 0, 0, and everything else would be a 1. Okay, how about for A bar or B bar? All right. In that case, what we're looking for is when would this inside here be a 0? Well, A would need to be a 1 and B would need to be a 1. When both of those are a 1, here and here, then that turns into the place where this is a 0, because 1 complemented is 0, 1 complemented is 0, 0 ordered with 0 is 0. Right, so that's the next step. Those two zeros are identified. So for B bar or C bar, we're looking for the place where B is a 1 and C is a 1. Okay, so hovering over this, you see 1, 1 right here on this row, and also 1, 1 right here on this row. All right, so that determines where all the zeros are within this logic expression. Then how do we read off the columns to propagate this to the output? All right, so we propagate this by looking at each of the columns, and if there's a 0 there, that's going to dominate because this is an AND term. You need all ones for the ones to flow through to the output. Okay, so as we see here, anytime there's a 0 in any one of the columns, the answer turns out to be 0. Okay, so this is an example of using truth tables. We're going to do this quite a bit, and often it's useful to construct a truth table with columns where it's easier for you to mentally figure out what those columns are, and then we put these together across the different columns to come up with the logic function that we're trying to find the truth table of. So hopefully this is helpful to give you an idea of how to construct valid truth tables.